Hello. So last time we saw that one can realize abstract group elements as concrete, say matrices, rotations, and all that. And I told last time that we are going to learn representations in this lecture, mathematical concept of representations. So what I have is a group, and representation is very simple. It's nothing but a homomorphism from G to GLN, say complex numbers. C is field of complex numbers. So that is a representation, quite simple definition. It's a homomorphism which starts from G and which takes values in GLNC. So what is this? This is our attempt to realize any abstract element in the group as a matrix. What's the advantage? We'll see after some time. So what are the examples? Some easy examples we can see. We can think of, you remember signature map or a parity map which takes value in, I had told you, say 0, 1. 0 is even parity, 1 is odd parity, and that can be thought of as a representation because I can think of 0 as say multiplicative identity and 1 as this minus 1 0 0 1, and that is a sub of GL2C. That's very straightforward example. Or simply you could have originating from any group trivial map. That is also example of representation. When you have Rubik's group, for example, and when you map an abstract state of Rubik's group to a concrete matrix which corresponds to that permutation, that is also an example of representation. Few more examples. This time let me just concretely take S3. So from S3 to this time I am taking values in GL2 of C. So I can think of S3 as permutation of 3 objects or permutations of, or the rotations of rotations and flippings. So symmetries of triangle. So there are 6 symmetries of triangle, and accordingly you map it to corresponding matrix. So let me just write it in this form. Maybe you have 1, you have 1 2, you have 1 2 3. So 1 2 2 3, 1 3 and 1 2 3 and 1 3 2, like this. So I can map it to, so 1 I can map to identity matrix, 2 by 2 identity matrix, 1 2 for example, 1 2 I can map to matrix which swaps your first and second rows. So it is just so I am having in GL3, sorry, I am having in GL3 I3 I3. So it's just swapping 2 rows, say 0 1 0 1 0 0, and then you have 0 0 1, like that. So corresponding permutation matrices. So Sn goes to, in general, corresponding permutation matrices. So that's also a representation. There are much more interesting representations. For example, when you have Dn, which are what? Symmetries of regular n-gon. So from Dn you can give a representation which is taking values in GL2 of C. So what is this representation? It just, again, it's a kind of permutation. So when you have say for example the square, say n is equal to 4 case, there are 4 states. So suppose this is identity, it goes to 1. So there are 4 cyclic, right? So suppose this is the state where 1 goes to 2. So 1 is here, 2 is here, 3 is here, 4 is here. So it goes to minus of identity. So this 1 is actually 2 by 2 identity matrix, minus I is the scalar, minus I 0 0 minus I, or you could have done it I also, doesn't matter, I or minus I, and then now 1 goes to, so 1 2 3 4 like that. So here it is minus 1, which is minus 1 0 0 minus 1, and similarly you have 1 here, 1 2 3 4, and that goes to say I, which is I 0 0 I, and then the flipping one, the one when this is flipped. So I have this. So flipping could be 2 here, 1 here, and 3 here, and 4 here, and that goes to say flipping of this thing. So this goes to 0 1 1 0, and then other you can obtain by appropriate composition. So whatever is actually happening for the definition, the way Dn is constructed, just by taking regular n-gun and considering symmetries. First you put all the cyclic orientations, all cyclic configurations, and then flip it, and then once more all cyclic configurations. And the way Dn is defined, using that you can define a representation. Here is an important concept for representations, which is that of character of a representation. So what do we mean by character? Character is a map from G to C. So I have a representation, let me call it F. The representation. So given this representation, I can associate to it a map, maybe I call it chi F. It's called character of f. What it does is, given g to it, so given g it associates to it. So you consider this fg. Fg is a matrix. So I can think of trace of this matrix. I can think of trace of this matrix, right? And that comes with the various interesting properties. So this is called character. So G going to trace of the corresponding matrix. Character is quite useful in understanding groups, in understanding conjugacy classes of groups. Useful in understanding groups and its conjugacy classes. And in fact, this notion of what are called irreducible representations is very central to theory of characters, to the theory of representations. So what is an irreducible representation? So I have, say, this representation. So I can think of GLNC as a matrix, or I can think of it as automorphisms of the vector space Cn. So Cn is a vector space. I could have said Rn, but theory over R is slightly complicated. Theory over complex numbers is quite straightforward. So you can think of it as linear maps from Cn to Cn. So I say that, when do I say that a representation? This F is irreducible if you consider a subspace in this. So F is irreducible if a subspace which satisfies that FGW is contained in W. So called stable subspace. So if stable subspace is either Cn or a trivial one. So it's very clear that if I have subspace, zero subspace, then any matrix over 0 is going to be 0. Any matrix over the whole thing is again going to take it to Cn, within Cn. But if you can get some non-trivial element, non-trivial subspace which satisfies this property, so non-trivial stable subspace, then the representation is not going to be reducible. So it is reducible if whenever you have stable subspace, then there are only two options for stable subspace, either this or this. So it so turns out that every representation is made of these irreducible representations. Every representation is actually what is called a direct sum of irreducible representations. So I am not going to say all that in detail. Every representation is direct sum of irreducible representations. And here is very interesting thing. Uh, Theorem, quite interesting thing, which says that number of irreducible representations of finite group G equals number of conjugacy classes of G. What are conjugacy classes? You have a group and you break it into partitions. On what basis? Two elements are in same partition if they can be obtained from each other by conjugation. So any two elements here are conjugate to each other, any two elements here are conjugate to each other, and like that, with that kind of equivalence relation, you partition your group and each partition is conjugacy class. So how many conjugacy classes are there? It's actually same as number of irreducible representations. And in fact, easy thing for us is to realize that if you have a character, you evaluate it on an element, or if you evaluate it on a conjugate element, answer is same complex number is there, because if you have two different matrices, if they are conjugate to each other, then their traces are also same. So chi f is just about taking a trace. Now theorem is that two elements G1 and G2, they are conjugate to each other if and only if chi f G1 is same as chi f G2 for every irreducible representation f. So if for all characters, all irreducible characters, if you are having same value of characters for on these two elements G1 and G2, then they have to be conjugates. So one can think of what is called character table. And what does character table do? So here you have characters, here you have conjugacy classes. Say here's the conjugacy classes of G, here's a character corresponding to a representation, irreducible representation G. So these are irreducible characters which are corresponding to irreducible representations. So here your entry will be chi f G, and like that you will make a square matrix. Why is it square matrix? It is square matrix because of this equality. Number of rows is same as number of columns. Number of rows is number of irreducible characters and number of columns is number of conjugacy classes. So therefore, to each group you can associate this data which is called character table. There are various interesting properties of character table. For example, character table is actually an invertible matrix. You can think of it as a complex matrix, right? And this is actually invertible matrix. Quite interesting property. Important thing is that you can read lot about a group. You can understand various properties of groups via character tables and via in general theory of characters. So some remarks I would mention. These are accomplishments of representation theory or character theory. So there are various problems in group theory which are otherwise difficult to deal with, but using the concept of representations of characters, one can easily deal with those problems. And I'll just tell some historical example. What is called Burnside's PQ theorem. What it says that if you have two primes and you have a group whose order is p to the power a, q to the power b. That means in the factorization of group, there are not more than two distinct primes which are occurring. So this is just the information on the order of the group and nothing else. What is surprising is that from this you can conclude that your group is having very special property of being what is called solvable group. Solvable group can be understood in terms of what is called a chain, a descending chain of groups, the derived chain of group. But let me just say that the solvability has something to do with the solvability of certain polynomial. So this is the property of groups. So solvability is a property of groups, important property of groups that has genesis in theory of equations, theory of polynomial equations. Quite important property of groups. So Burnside PQ theorem actually is a statement purely in group theory, but one can prove it using character theory. Another interesting problem which I would mention is quite curious. You take G group such that the order of the group is odd, and then you say N is number of conjugacy classes. In general, computing number of conjugacy classes is not straightforward for a group. Statement is that if you consider G and you consider N, this is a relation. G is actually congruent to N mod 16. Quite curious. Number of conjugacy classes and number of elements in the group, the difference is always divisible by 16 provided your order of the group is odd. This makes use of what are called real representations, rather real characters, and so-called real conjugacy classes. I won't say much in detail, but the message that I want to put forth is that you have a group, it's an abstract group, you find ways to understand it, you find different representations of it. Sometimes those representations could be tangible, they could be there in the real life. All the examples I have given earlier through puzzles and toys and some symmetry considerations. And sometimes you can realize, you can represent those groups in terms of matrices, and if you analyze those matrices close enough, then you can then it can reveal lots of interesting properties of groups. Representation theory is quite a wide subject. I'll just try to give a flavor of that, And in fact, not just for groups but for other objects in mathematics as well. There is representation theory, and it has its own ways of characterizing reducible representations and all that. And purpose of any kind of representation theory is essentially to understand your original object much better, and quite often in some combinatorial way or in a way where making computations is quite handy. So I hope you could follow somewhat. In coming lectures, what we are going to understand is something more about this particular group. And as I said, this is a group of rotations in R3. So some interesting things are coming up, and those things will have some nice, they are coming up as a nice application of group actions. So be with me. Thank you.